So let's take a look at field energy, and in particular we're interested in the energy of the electric field involved with dielectrics. We're interested first in how much work it takes to assemble free charge. So if you bring in some free charge, the dielectric responds. What happens, of course, is some sort of polarization occurs that involves the presence of bound charge, so that will change as we polarize. We will consider this later, but right now think of it as showing up as part of the potential that is being used in the media itself while we're trying to put free charge on. So if you look at that potential as a function of some vector r prime, there's a free charge density, again as a function of r prime. Remember when we had this for vacuum, the work to assemble the free charge was equal to this integral times a half, where we integrate over the charge density times the potential over the volume d tau prime. And all of this is enclosed in a volume tau prime. And remember that this V is due to all the charge. This was by analogy from last semester, because we're going to be doing cases where this is not for free space but also for the dielectric. We can relate the charge density to the displacement vector. If you remember, the free charge density is equal to the divergence of the displacement. We can put that in for rho sub f right here, and so I've just switched the order. Here's V times the rho sub f. So now we'll use a vector identity, which is basically a function of a function. So here we have a function times a vector, and we're taking the divergence of that. So that's equivalent to doing the derivative of a function of a function. So when we do that and reorder, then we can end up with a term which is what we want for the work integral up here. So substitute in this term minus this term. We have then that the total work done is given by one integral here and then another integral over here. I just want to remind you, this is the work to assemble the free charge in the presence of the dielectric. One more time, the dielectric is responding to this free charge through polarizing the dielectric and at the same time the associated formation of bound charge. So now we'll use the relationship between the E field and the potential, and we'll also use the divergence theorem. We have here the surface integral of Vd dot ds, where what we've done is we've converted the volume integral to a surface integral for this particular integrand. The other one is exactly the same that we had before. It's important to remember that this E is E total, so it includes the bound charge. We want to get rid of this first term, and if you remember, S prime is the surface enclosing tau prime. So what we're going to do is let tau get really big, so it's like bigger than the universe. Inside tau prime, any interesting problem will have D and E non-zero. Normally those are in the same region of space, so the D dot E is not equal to 0. The importance of that is that this term here, since we're integrating over all volume, very, very large volume, we'll still have regions where this is non-zero. So therefore, those will contribute to this term right here. This term here, if you remember, we did similar things for the E field. If you have a particular voltage in terms of say a charge distribution, eventually the V will just simply go as the distance 1 over r. D and E go like a Coulomb's law, 1 over r squared. And ds goes as r squared. So you can see that you have a 1 over r times 1 over r to the 4th, and then times r squared. So we're going to have something that totally goes as 1 over r to the cube. If you take the limit of making r very, very large, say infinity, this first integral goes to 0. So we're only left with this integral here. So we end up with this equation here for the work done. If we wanted to, we can define this in terms of a density, an energy density. Let's just call it little w sub e. And if we integrate the energy density over the volume, that gives us the total work done. If we look at what this should be, then if you just go up here, you can see that 1/2 times this quantity here would be the little w sub e here. For a linear material, you remember that D is equal to epsilon E. So substituting that in, we get this equation for the energy density that's in the field. And just recall that the units for W sub E are energy over distance cubed. Alright, now this is pretty important, and I'm going to say this without proof, that the W sub E that we've worked out here is equivalent to the total W, which is the total work required to assemble the free charge in the presence of the dielectric and at the same time produce the response of the dielectric, which produces P in the bound charges. This quantity here, which we found from basically integrating the D field and E field, is equal to the total work that is required to assemble the free charge in the presence of the dielectric and produce the response of the dielectric. We can use this then to talk about the total energies. So here's the statement again. We can think of the dielectric response as a sum of strain energies. So as we bring in more free charge, it generates stronger and stronger dipoles, and those of course are in the material. So what we are doing is essentially separating, we can call it the bound charge, further and further apart. So this is like a spring. It's energy that's stored in terms of something like a 1/2 kx squared, where this is the displacement of the charge. So if we argue, like we did earlier, that the work done to assemble the free charge is equal to the increase in potential energy stored in the fields and the springs, we can state this in terms of densities. Then we have in magnitude that the energy which is developed in terms of the work done is equal to the potential energy that we put into the field. And the same goes for the densities. This was the work done per unit volume, and this is the potential energy per unit volume. And realize that these are spatially defined. As you go around in space, you'll have this quantity changing, which is equal to this quantity. So if you take this classical model that has these springs, the energy density, which is what we're going to say is the total, is equal to this quantity here, which we've already shown. This is the E total, which is the bound charge E plus the free charge E. And that is equal to the energy density of the field plus the energy that's stored in the springs. And that's the total energy density. So let's take a look at a parallel plate capacitor. Consider that the capacitor has a dielectric constant epsilon, which is equal to the relative emissivity times epsilon 0 and permittivity, and so this is the total permittivity. E sub r could be 1, in which case you're in a vacuum. We're going to ignore edge effects, so all the field lines are perpendicular to the plates. There are no fringing fields. And the battery, if we place a battery across here, is what drives the free charge out onto the plates. So this will have plus K free and this will have minus K free. And of course really they're located on the inside surfaces. And we're going to take the area of the plates as A and the spacing D. If we go for linear dielectrics again, this simple geometry has D equaling sigma free, where sigma free is the total free charge divided by area. E total, if you remember, is 1 over epsilon r times E free. So if we substitute in E free as being the free charge density on one plate divided by epsilon 0, you can see that we now have E total, which we can put into the total energy or total potential energy equation. So this would be 1/2 d dot E d tau. Take our problem here. Here's the parallel plate capacitor version of this. So we have the total energy that's in the fields, which is 1/2 times D times E total times A times D to get the volume that we're dealing with. This is energy density times the volume, and that'll give us the total energies. Substituting in our D and E values, we get the same quantities equaling to 1/2 sigma free 1 over epsilon r sigma free over epsilon 0 times the volume. One more time, this is coming from D, and all of this is coming from E total. Times the volume gives us the total energy of the field. So when you simplify that in terms of Q free over area is the sigma free, the work, which is equal to the U sub E with the dielectric, is equal to 1/2 q squared free over 2, and then epsilon r, epsilon 0, a over d. And I put everything in this form, so I brought d down below here, because this right here is the capacitance with dielectric. Or if I take epsilon r out, so I have epsilon 0, a over d, that's the capacitance with no dielectric. Continuing on then, what we have here is that the energy, the potential energy in the system is 1/2 times q squared free divided by the capacitance with dielectric. And so this is a pretty important equation for finding the energy that's stored between the parallel plates of a capacitor with a dielectric. If you take the energy without a dielectric, you'll notice that all you're doing is multiplying by 1 over epsilon r. When you look at the energy densities, if you have the same free charge, the energy with the dielectric is actually less than the energy without the dielectric. We consider C to be whatever it is, with or without a dielectric. When we put charge on a capacitor of either type, we always get the free charge that we're interested in onto the plates. So we've already shown that that's equal to 1/2 q squared over c. And so now if we just use this relation here, we can basically find 3 versions of this equation. There's this one here. If we eliminate q, we get this equation. And if we eliminate capacitance, we get this equation. And remember, with a dielectric, it's C with the dielectric. You might say, well, wait a minute, this is Q free, what about V? Well, don't forget that if you have a Q and a V, then that is actually going to depend on the presence of a dielectric, and so that's why this is fine. We can get the stored energy in a capacitor a different way. This is done by looking at the work done, or the power expended, and then integrate over time in putting the free charge onto the plates. So we'll call that Q. How does that work? Well, here's the work done by the battery, right here, and that's equal to the power expended by the battery, integrated over time. To get all the power expended, we're going to go from t equals 0 to infinity. What is the power? Well, it's V times I dt. As a function of time, this is the power. One or both of these could be changing with time. So let's go to the voltage equation for the system. That'll be the Q that's on the plates, which might be increasing, for example, with time, divided by the capacitance. And the current is defined as the rate of change of Q with respect to time. If this is very high, you have high currents. If this is 0, this is 0, and so on. We go back to our power expended. That's what this is right here. Integrate over time. We can see as a constant, so we can bring it outside. I put primes on here because these are dummy variables. So this will be q prime dq prime from 0 to q, the final q, and that's equal to q squared over 2c. Does that look familiar? Well, let's see. Like above, we have then that this value, which is equal to the potential energy put into the system, is equal to the same equations before, and then we can use the C equals Q over V to get these two versions here. Now if we go back to the parallel plate capacitor, if we want to put in C equaling this, where for the dielectric we just have an epsilon here, the voltage is the total field in the dielectric times D. This is important that you understand that. And so then you can substitute in for C and V into this equation here. You'll have 1/2 epsilon A over D, that's C. For V we put in E total times D. Square it and simplify. So what we get is this quantity here times a volume. So this is the energy density. If you go back here, U sub E is equal to epsilon E total squared over 2, which is what we obtained above. This is just a more general result. So given this result, if we have E with the dielectric equaling this quantity here, and we know E total is 1 over epsilon R E free, then we can compare this with the field as if there was no dielectric. Go back here, put in E free and epsilon R, and so you look at this energy density here, which we've derived already. You put that in and you get a very simple relation where you just have 1 over epsilon R times U free. If you now integrate over the volume, you'll get the total potential energy with the dielectric, and that's 1 over epsilon R times the free value. So if you had no dielectric, you would have this quantity here. So you simply divide by epsilon R to get the potential energy with the dielectric. So for a given charge, Q, the dielectric filled capacitance has less energy than the vacuum filled. And that's because you divide by this epsilon R to go from free to with dielectric. Going back to our U sub B equation where we had Q squared over 2C equaling these other two terms, realize that if Q is constant and C is increasing due to putting in the dielectric, it lowers the potential energy. If V is constant and C is increasing due to putting in the dielectric, it increases the U sub B. Do not panic. We're going to go through this again where we actually take a parallel plate capacitor and push and pull the dielectric around. And so that brings us to the next time, which is may the force be with you. We're going to look at the force on dielectrics and see what happens.